Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so thank you all for coming. Today we're very pleased to have Eyal Goren visiting from McGill University. Eyal has been a frequent visitor to Microsoft Research, and we're very pleased to have him back. So today he'll talk about class invariants for CM fields of degree 4.
All right, thanks. So indeed, I visited several times before, but nonetheless, thank you again for the invitation and for coming to this talk. The tech people asked me if there are sound bites associated with the talk, and there are none, but in fact, maybe here and there I should have included sound bites of groans and frustrations and kind of pounding on the table. The problem of understanding class invariants for CM fields of degree 4 is just one step after understanding the situation for elliptic curves. But nonetheless, there's a series of new difficulties that are coming up, and in spite of a lot of work, we still don't understand the picture in this case. I'm going to speak about joint work with Deshalit, who was my thesis supervisor. That's where my interest in this project began. And most of what I'll describe is actually joint work with Kristin Lauter, who came to the same questions from a different angle. I was interested in constructing units in abelian extensions of CM fields. Kristin had some questions about constructing genus through curves with given number of points. And it turned out that the same questions arise in both circumstances, and that's how we got to collaborate on them. And Daniel Valliere is a student of mine. He's doing now his PhD degree in San Diego. And he calculates some interesting numerical data concerning the stuff I'm going to talk on. All right, so the thing with the Beamer that it produces for you a lot of slides which are a bit too conceptually organized for such a short talk, so I'll just go skim over them. Let us begin by the issue of constructing algebraic numbers. And I think it's fair to say that over a century, really, the strongest technique we have is taking modular functions like the J function or other modular functions and evaluating them at CM points. We get a lot of information about the action of the Galois group and other properties coming from work like Shimura's reciprocity law and more modern interpretation of modular functions as functions over schemes that parameterize elliptic curves or abelian varieties with extra structure. And the prototype or the basic example is taking a tau in the upper half plane such that the corresponding elliptic curve has complex multiplication, say by the full ring of integers of a quadratic imaginary field. Then, in fact, if we adjoin to k the value of the J invariant of tau of that elliptic curve, we get the Hilbert class field of k. It's a fantastic result that gives the flavor of the whole subject. The question is, well, once one knows this result, how can we generalize that? And there are many directions known by now, and let me quickly go over them. First, backtracking a little bit, instead of taking CM by the full ring of integers, we might take CM, namely assume that the elliptic curve has more endomorphisms, where the endomorphism ring is not the full integer ring of k, but a smaller order. And then we get a ray class field of k. But we might think about generalization in the sense of using other modular varieties. So one can use other modular curves, like x naught n, and so on. The same points are still associated with k, which is a quadratic imaginary. So we don't get new cases this way. Or we could take Shimura curves associated with indefinite quaternion algebras over Q. And then the CM points on them turn out to be biquadratic CM fields. So they are composites of quadratic imaginary fields. And we know by that, we know already a lot about class fields for those fields by using what we know about quadratic imaginary fields. New cases come up when we consider Hilbert modular surfaces. So those are surfaces that parameterize abelian surfaces with a given endomorphism ring, or a better way to say it, with such that the endomorphism ring contains the ring of integers of a real quadratic field L. So to simplify, I'm assuming that the strict class number of L is 1. Okay, so we're looking at abelian surfaces such that each abelian surface actually has inside its endomorphism ring the ring of integers OL of L. And the complex points are sort of a generalization of what we were looking at. The usual modular curves, you get the upper half plane modulo SL2Z or subgroup of SL2Z. Here you get two copies of the upper half plane modulo the action of SL2 OL acting in a diagonal way. And there's interesting structures on those surfaces. There are certain divisors on those surfaces called the Hirzebruch-Zagier divisors. And their components, we should think about them as divisors that are associated to previous moduli spaces we have discussed. So in fact, it's a way to group together certain curves lying on those surfaces, such that each Tn is highly reducible, but they're just indexed by integers. And those Hirzebruch-Zagier divisors are grouping together components which are either Adler-Shimura curves of this type or modular curves of this type. Okay? There's some algebra behind it. And now we're getting what I will call primitive CM points. So we're getting fields which are quadratics, namely degree 4 CM fields over the rational, but now they are primitive in the sense, in this case, we can define primitive to be just not biquadratic. In general, if we talk about CM fields of any degree, the notion of primitivity is not quite the same. But for fields of degree 4, it just means not biquadratic, which means that we're really dealing with a new case. We can't use any more quadratic imaginary field to get a handle on what's happening with extensions of K. And there exist functions on those surfaces whose divisor is a combination of those Hirzebruch-Zagier divisors. And in that sense, they are good modular functions. In what sense, good is used here? Well, it will become clearer a bit later. Okay. So, but the structure is we have those surfaces. We have a new kind of CM fields appearing, the primitive quadratic CM fields, and there are functions that their divisors they vanish or are zero exactly on the Hirzebruch-Zagier divisors, which are of interest in this game because they themselves have a modular interpretation. Okay? So there's like a hierarchical structure here. Another way one could generalize is to go to the Ziegler space, which just parameterizes abelian surfaces. Principally polarized, but if you haven't seen it before, don't worry about it. Okay? So you just look at abelian surfaces. There's a difference between this and what we just talked about. We don't assume anymore that the abelian surface has multiplications or endomorphisms by a given real quadratic order. Just abelian surfaces. And the complex points now are given by the Ziegler upper half plane, which is actually three-dimensional. So those are the 2x2 symmetric complex matrices whose imaginary part is a positive definite matrix. And there's the symplectic group in 4 variables, or 4x4 symplectic matrices act on this space in a way similar to the way SL2Z acts on the upper half plane, so kind of fractional linear transformation, so to say. And in there, we find similar structures. So inside this three-dimensional space, there are the Humbert surfaces, Hn. They are indexed by integers n, again, natural numbers n. And in fact, each Humbert surface is an image of a Hilbert modular surface of the kind we just described. And when you pull back those Humbert surfaces via such a map, this map just, in the terms of moduli spaces, what it does, it just forgets the extra information. So ML parameterizes abelian surfaces with real multiplication. And when we forget that, every point corresponds to an abelian surface, and that gives us a point here. Okay? There are natural maps like that. And in fact, the hierarchy is preserved in the sense that if we pull back the Humbert surfaces, we get a sum of those Hirzebruch-Zagier divisors. Okay? So this whole thing is kind of consistent picture. And in fact, also in this case, there are good modular functions or modular forms. There are Siegel modular forms whose divisor is a certain multiple of Hn. We can't necessarily get Hn on the nose, some positive multiple of Hn. And those forms, we take those that, making An as small as possible. And then this form has a certain weight. Let's just call it Wn. Those weights are actually quite interesting numbers, but I'm not going to go into their description. Okay? So that's another place where one can look for generalizations of this technique of constructing algebraic numbers by evaluating functions on moduli spaces. The functions we could look at would be such that they are supported, their divisor is supported on those Humbert surfaces, and we can evaluate them at those primitive CM points associated to quadratic CM fields. So the main example for this talk would be the following. We have the Humbert surface H1, and there's a modular form delta 1 that vanishes to order 2. It has weight 10. And there's a precise formula for it. Those are the Riemann theta functions, the 10 even Riemann theta functions that we square each one of those. So each one has weight half. When we square it, we get weight 1. There are 10. So the weight of the whole product is 10. And we normalize it by this factor to make sure that the Fourier coefficients are not just integral, but relatively prime to each other. Okay, so this is an example of such a modular form. You can write it explicitly. You can implement it and actually evaluate it at certain points. And this H1 is an analog of this image of a modular. Remember that the HNs were in some cases images of the Hilbert modular surface. In some sense, it's an analog of that. The divisor of delta 1 also has a modular interpretation. It actually parameterizes pair of elliptic curves with a product polarization. Okay. And that's actually true in every characteristic. So what do I mean by that? The divisor, here I'm looking at a complex function, and its divisor where it vanishes. And if you interpret the moduli, the Siegel moduli space as a scheme over Z that parameterizes abelian surfaces, you can take the closure of this divisor, and in every characteristic, it will parameterize pair of elliptic curves with a product polarization. Okay. And as good functions, we can, for example, take functions of the following sort. So if I have delta n vanishes on the Humbert surface Hn, I can take it to the power 10, and delta 1 to the Wn, so it's the same weight, and I get a function. So that's a function whose polar divisor has an interpretation given here, and its zero divisor, where delta n vanishes, also has a modular interpretation, which is abelian surfaces with certain real multiplication. Now the question, okay, where to go to next? So this slide is a little bit of a suggestion than results. Traditionally, people have looked at AG, the moduli space of G-dimensional abelian varieties, principally polarized. But the problem there is that as long as, I mean, as soon as G is big enough, greater than 4, we don't know anymore a choice of natural divisors like the Humbert divisors or the Hirzebruch-Zagier divisors, stuff like that. And we don't know any natural choice of functions on those spaces either. I mean, we know those are algebraic varieties, they're actually schemes over Z and a lot of things abstractly, but there's nothing that suggests itself, like the J function or generalizations of that, as a candidate to getting interesting number theory out of those spaces. And in my mind, there's a complete sort of revolution that have taken place or should take place, which is taking into account Borcherd's work. From the point of view of Borcherd's theory, I mean, we looked actually, in the cases where we know some stuff, we were looking at SL2L, where L is quadratic, that gave us the Hilbert modular surfaces, or SP4Q, that gave us the Ziegler spaces. And it turns out that those are forms of the algebraic groups SO22 and SO23. So there are those accidental isomorphisms taking place. And Borcherd's developed a theory that have to do, or got some striking results about the Shimura varieties of type SO2n. And if we consider the functions for which we know deep theorems, they all turn out to be special cases of Borcherd's results. For example, the function j tau 1 minus j tau 2 on h times h, where this is the j function, we'll see that this is really a function that has to do with results of Gross and Zagier and so on. This function, functions whose divisors on the functions on the Hilbert modular surfaces whose divisors are supported on Hirzebruch-Zagier divisors, or functions whose divisors are supported on the Humbert surfaces, all turn out to be examples of what's called Borcherd lifts. So Borcherd's produced a lift that takes elliptic modular forms, possibly of half-integral weight and poles and stuff like that, and produced from them modular forms on the Shimura varieties SO2n. And it turns out that the most interesting cases, the cases where we know sort of substantial theorems, are all examples of Borcherd's theory. So it suggests that really another natural direction to go is not AG, but the Shimura varieties SO2n, and it's kind of an invitation to anyone interested to start studying those spaces. They are not really studied so much nowadays, or I should say so far are not studied so much. The pros are that they come equipped with many what Borcherd called Higner divisors. They just come from embedding of algebraic groups. So examples of Higner divisors in Borcherd's language are the seam points on modular curves or Shimura curves, the Hirzebruch-Zagier divisors on Hilbert modular surfaces, and the Humbert divisors on the Ziegler space are all examples of those Higner divisors. And Borcherd's theory actually produces for us a lot of modular forms coming from elliptic modular forms. So we can calculate elliptic modular forms, and using Borcherd's theory we can get good candidates for functions for which I would expect that their values at seam points should contain interesting arithmetic information. The converse or the cons at these points are that we actually don't have all the machinery that we have in place already for modular curves or Hilbert modular surfaces. So I mentioned here a few issues that we don't know in general, but well, that's what research is about, to develop it. Right. So as I say, this slide is sort of an invitation. I'd like now to go back to functions, for example, like the function that appeared before, this delta 1, or functions of this sort, phi n, and explain a little bit of what we are using in our research. So the main point is, if we have a CM point on A2, on the Ziegler space parameterizing Abelian surfaces, and suppose that this point does not lie on Hn or H1, you make a picture. And so here we have A2, Here we have, say, Hn. Here we have H1. But we can think about everything as happening over spec Z. And those actually, you should think about them as existing in every characteristic. Okay, so this is over prime P. And I take a point. So I have a function whose divisor is supported on Hn and H1. And I take a point, a CM point, outside it. And it might mod P intersect either this divisor or somewhere else, the divisor of Hn. I mean the Hn. And one of the main tools we are using is this arithmetic intersection theory that tells you that if you take a function like phi n, whose divisor is basically Hn minus H1, then if a prime P divides the value of this function at the same point tau, it means that when I take the associated Abelian variety, remember that on a moduli space, every point has an associated object. So this has an associated Abelian variety, A tau. Then it means that if I take this Abelian variety and reduce it mod P, it will lie on Hn. Okay? Hn has a modular interpretation. To say it lies on Hn means that it has certain real multiplication. If it appears in the denominator, then it means that mod P, it belongs to H1. Okay, and for H1, let me just run through the analysis with you. So to say it's in H1 means that mod P, H1 parameterizes this data. So it means that this Abelian variety becomes isomorphic to a product of elliptic curves with the product polarization. And if you wish, since every principally polarized Abelian surface is a Jacobian of a curve, uniquely determined by Torelli's theorem, it means that if we take this curve, which actually has a model over a ring of integers, and I reduce it mod P, well, the Jacobian of the reduction mod P should have this form, and it turns out that that imposes that the curve mod P is actually isomorphic to two genus one curves crossing transversely. So it imposes it tells you that mod P, this curve, is singular and of very, very specific kind of singularity. So basically, the analysis we're going to discuss, or most we're going to discuss today, has to do with this. Actually, so phi n, remember, was the function whose numerator, whose zeros were Hn, and denominator is always H1. Okay, so we're going to look at such issues. When is it possible that a tau mod P is isomorphic to two elliptic curves with the product polarization? Okay, now a slight disadvantage in using the functions phi n, that to understand their values, we have to do two problems, two moduli problems. One is to understand mod P, whether it has real multiplication, and then to understand mod P if it has this property. And there's a variant considered by the Shalit and I where only the function delta 1 is being used. So the problem really, we are able to deal just with one moduli problem instead of two. In fact, we're just able to deal with the simplest moduli problem, which is when is A tau mod P a product of elliptic curves. So I'll just give you just a sample case of the construction we are doing. So to fix ideas, let's assume that we are dealing with a primitive cyclic CM field. So it's degree 4 of the rational numbers, which is an abelian cyclic Galois extension. And the same setting as before, so the totally real subfield is L, and I assume it has strict class number 1. And then we have a way, given a pair of ideal classes of K, to produce an element, a non-zero element in the Hilbert class field of K, basically just by evaluating delta 1. So there's a way, and the exact description is a little bit technical, so I'll refer you to the paper. But if you have two ideals, A and B, or two ideal classes, we can somehow play with them and their product and OK to calculate basically delta 1 on 4 different lattices, such that the value in the end is well defined and depends only on the ideal classes A and B. And we get a number that we can show that it lies in the Hilbert class field of K. Okay? Those numbers were an attempt to construct units in abelian extensions of such CM fields. So for the rationals, we have a wonderful theory of the cyclotomic units. And for quadratic imaginary fields, there's the theory of elliptic units, which is very, very well developed. And the interest was to try and construct units for other fields. For example, some motivation was for Stark conjectures, where values of L functions are supposed to be associated with units of the field, and those conjectures are completely open in general, and we wanted to get units that could possibly be related to values of L functions. So that was an attempt, and well, first of all, we got a number which is not 0 or infinity. That's a good first step to construct units. The Galois action is given in a very elegant formula. It's basically a sort of a co-cycle operation, where the action of the Hilbert symbol acting on this UAB is given in a ratio of those two pseudo units. So altogether, it's kind of a co-cycle relation that we have. It has the group generated by those elements is a pretty high rank, but not as good as one would like, in fact. If you norm those numbers down from the Hilbert class field to the field itself, you get 1. So it's similar to what you would get if it was a unit. And we also at that time had the information that the prime that divides those numbers is either ramified in K or splits in K. So some arithmetic information about which primes can arise. Now, the main point here is, I should mention it already here, that we can prove, and the argument was given in the paper of Kristin and myself, that if those invariants UAB are not units, it has to do with the same problem we've seen before. Namely, if UAB is not a unit, it means that there's an abelian variety with CM in K that mod P reduces to the divisor of delta 1. Namely, mod P becomes isomorphic to a product of two elliptic curves with the product polarization. So let us look a little bit, and I'll explain. Basically, I want to explain this. Okay? So if a prime divides UAB, I say it's either ramified or split. Let me give you some feeling of how it goes. So as I said, if it divides UAB, the issue is that the abelian variety mod P becomes isomorphic to two elliptic curves with the product polarization. But let's forget about it. Just the fact that it's isomorphic to two elliptic curves, well, first of all, because A has complex multiplication, it means that K embeds into this endomorphism algebra. So first, the elliptic curves have to be isogynous. Okay? If they are not isogynous, there are no maps between them, it would imply that K embeds into N0 of E1, say. But an elliptic curve cannot have so many complex multiplications. So they must be isogynous. And if they are ordinary elliptic curves, then their endomorphism algebra is just K1, some quadratic imaginary field. And then we get an inclusion of K into M2 K1. That would be this. And that implies, by easy algebra, that K1 embeds in K. But that actually implies that K is not a primitive CM field. It implies that K is a compositum of quadratic fields. I mean, namely K1 and its totally real subfield. So that cannot happen. so it follows that if there's an obstruction for the UAB to be units, namely if AT mod P is E1 times E2, then the elliptic curves have to be supersingular, and therefore this abelian variety is what's called a superspecial abelian variety. Okay? So maybe I'll remind you of the terminology. In characteristic P, if A is isogenous to a product of elliptic curves, then it's called supersingular. And if A is isomorphic, and there's a big difference between the two, then it's called superspecial. Okay? And there are two invariants that one can associate to abelian varieties. So this A, the A number of A is, well, there's no easy way to define it really. But it's the maximum A such that you have alpha P to the A sitting inside the abelian variety. So it's the maximum of A such that this happens. And the F number of A, it means that P to the FA is the number of P torsion points of A defined, say, over FP bar. Okay? So it's how many physical P torsion points you have. Those are two discrete invariants one can associate to any abelian variety, and it gives you a rough classification. For example, if you look at elliptic curves, if the elliptic curve is ordinary, then the F number, I should squeeze it here. So this works for any, if you look now at the elliptic curve, if it's ordinary, then F is equal to 1, A is equal to 0. And if it's supersingular, then F is equal to 0 and A is equal to 1. And you know that using complex multiplication, you can distinguish between the two things, the possibilities, just based on how the prime decomposes in the CM field. So there's a similar phenomena in this case, that just using the fact that A is complex multiplication, we can determine those invariants mod P. And it turns out there are 4 possibilities, 2, 0, 1, 0, 1, 1, 0, 2. From the theory of abelian varieties, you can see there aren't any more possibilities. This case actually doesn't occur in the case of cyclic fields like the one I'm considering right now. In the superspecial case, so the same analysis using the theory of complex multiplication tells you that the prime decomposes in such a way. The prime is completely split. It turns out you get an ordinary reduction, and if the prime is inert, you get something which is supersingular but not superspecial. So the theory of complex multiplication gives you this a priori information about which primes can divide the UAB. But here comes the mystery that we know the UAB are algebraic numbers. And we know, therefore, that there are only finitely many primes that could divide them. So it means that there are only finitely many primes such that AT mod P, where AT is any abelian variety with Cm by K, is isomorphic to a product of elliptic curves with the product polarization. Okay, but here we get the reduction, namely the phenomena that it's just isomorphic to a product of two elliptic curves, supersingular elliptic curves, happens infinitely many times. I mean, any time prime decomposes this way. Okay? So there's a real difference between being isomorphic to an elliptic curves, a product of elliptic curves, and being isomorphic together with the polarization. Okay, and that's some of what I call the mystery of the situation. Okay? There are only finitely many primes such that this isomorphism holds with the polarization, but otherwise it could hold infinitely many times, just that it's a product of elliptic curves. It's sort of interesting that there are about p squared over 72 pairs of I mean, if you count how many you have, principally pairs of Abelian surfaces you have of the form E1 times E2 with the product polarization, there's about p squared over 72. But if you count how many principally pairs super special Abelian surfaces there are, you get p cubed over 2880. Okay. So the ratio is about p. So it means, it seems that from this, the probability of a prime dividing UAB is about 1 over p. And there's no reason for those things to be dependent of each other, and some 1 over p diverges, right? So it seems that we don't have enough information here. And what turns out in the end of the day is that there are, in fact, strong restrictions on those two elliptic curves. They are close to one another in some sense, and then if you do the probability, you get a converging sum. So, but that just gives you a hint that we still don't understand completely this phenomena of being isomorphic to a product of elliptic curves with a product polarization. Right? And as I said, the relevance to that is if UAB is not a unit at P, then some AT with CM by OK is isomorphic to such a product. Right, so I'm still at that part of my talk that has to do with motivations, and I think I'm going really over time. Yeah. Okay, so let me quickly remind you, if you look at elliptic curves with CM and you want to construct such an elliptic curve with CM, then to construct it is basically to find its J invariant. But that's an algebraic number. So what does it mean to find it? Essentially, it means to solve or take a solution of its characteristic polynomial. In fact, this is the minimal polynomial. And so if you look at such polynomials, the theory of complex multiplication first tells us that it's a rational polynomial because, in fact, the Galois group acts transitively on those J taus. But it tells us more than that. It tells us that in fact, every J of tau is an algebraic integer. That has to do with the fact that every elliptic curve has potentially good reduction. So it means that we can actually calculate this polynomial numerically. Okay, we just run over all taus in the upper half plane with complex multiplication by k up to natural equivalence. And that's easy to do. It's basically the theory of reduction for binary quadratic forms. It's easy to find those. And then we can calculate this in an approximate manner. But we know that we should get integers. So if we have control over the error, we can actually recognize the polynomial very quickly. And that actually allows us, in practice, well, I guess the experts are really in the audience. But well, I'll take the chance, but it allows us to calculate it numerically quickly over the complex numbers, and therefore to construct this elliptic curve explicitly. One way this comes up is the following classical problem arising in crypto or various applications of elliptic curves, like for factoring and so on, is suppose you want to construct an elliptic curve over Fp, with a given number of points, p plus 1 minus ap. And we know that this ap is bounded by 2 square root of p. That's the Hasse bound. And one technique to construct those is, well, first one observes that it's the same as to construct an elliptic curve over fp with an endomorphism satisfying this equation. Okay, that's a bit of a leap, but if you have seen a bit of elliptic curves, that's kind of probably known to you. This phi must then be the Frobenius endomorphism of the elliptic curve. Okay? And then comes, another big leap that it turns out that it's the same to construct an elliptic curve over the complex numbers with an endomorphism satisfying this. Okay, and it uses some heavy theorems to go from this observation really to this theorem that it's enough to do this. Okay, so it's the whole Dorian theory of seam lifts and the whole theory of complex multiplication going in the other direction. But from a practical point of view, perhaps you don't care, and you just look at this problem, how to construct such an elliptic curve with an endomorphism satisfying such a polynomial. And, well, think about this phi now as a complex number, and then it's very easy. I mean, you just take C, the elliptic curve C modulo the lattice, where the lattice is Z plus Z phi. So phi acts on that, obviously, because it takes Z to Z phi, and it takes phi to phi square, which is a combination of phi and the integers. Okay, so obviously it has multiplication by phi, so there's an endomorphism satisfying this equation. And then what you want is to calculate the J invariant of this elliptic curve, and that's the problem we just discussed that you can do with those Hilbert class polynomials. Okay? So this is a sort of, I think, a rather beautiful solution to this problem, and asking those problems in the genus 2 curves as well. That's a problem Kristin worked a lot on, and so many of our projects were sort of at least initially motivated by questions, some questions coming from this direction. So what happens then? Well, Igusa showed that in fact, there are analogs to those J invariants. I'll just call them H1, H2, H3. And the curve is known by the value of the functions H1, H2, H3 in the same way an elliptic curve is known by its J invariant. So if I have a curve C and I take its Jacobian, it's parameterized by some point on the Ziegler space. And as I said, the point and therefore the curve are determined by finding those numbers, by those numbers. Where actually doing it in practice requires a lot of work and clever ideas, which I'm glossing over. So then you're led to consider those Hilbert class polynomials, which are analogs of the polynomial we considered for the J function. Okay? And again, to solve, I think, so that's somehow Kristin's work to a large extent, is to find, to use this method to construct curves of genus 2 over a finite field with a given number of points. And therefore, what you want to do is numerically evaluate those polynomials. Okay. Or numerically construct those polynomials. And again, the theory of complex multiplication will give you that those are rational polynomials, but unlike the case of elliptic curves, you don't know those are integral polynomials. There are denominators there, and I think actually Marco looked at this problem of estimating the running time to calculating those polynomials. So the issue here is, and that's how somehow it's exactly the point where Kristin and I started collaborating, is that we ran into the same obstruction. Those Igusa invariants are certain modular forms divided by delta 1 to some power, where delta 1 is the same modular form we discussed before. And therefore, the denominators have to do with the same problem, with the existence of Fabian varieties with Cm, by the field you're looking for, that mod P become isomorphic to a product of elliptic curves with the product polarization. Okay? And as I said, there are no sound clips in this talk, but if there were, there would be a huge groan here. And it's working at some point after working on that for several years, we just called them evil. Okay, so that's kind of, I think, embodies the frustrations we felt. Okay, so we call such primes evil primes. The notion depends on K. Those are primes for which Abelian varieties with Cm by K become isomorphic to a product of elliptic curves with the product polarization. There are finitely many such. Okay. So here's a bunch of questions one can ask. Well, first, do they exist at all? Are there evil primes? Do they exist for every field K? For which field do they exist? Can we say how many there are, or how large they are, or give any other information about them? And so you can ask for bounding them, and then you can ask how many there are within this bound, and so on. And finally, you might strive to understand in which way they arise. Okay, so those are different questions. Okay, so I don't have time right now to present the data. I'll just say that there was data obtained by Paul van Wemelen many years ago, I guess about 12 years by now, that show that evil primes exist. Okay? He calculated those Igusa invariants for CM fields of degree 4 over the rationals. I mean, CM fields of degree 4 over the rationals. Actually, that also had class number 1 or 2 and very specific situation. But he got primes in the denominator, so we knew those existed. But when we looked at the invariants de Chalit and I constructed, those UAB, they involved 4 different abelian varieties. There were 4 lattices there, OK, A, B, and the product AB. So one could hope that maybe there's a cancellation of the primes. Turns out the situation is not like that. It's another groan, big groan. And that was calculated by Daniel Valliere in his master thesis. And in fact, the data is obtained and inspired us to prove some new theorems about those invariants and those evil primes. All right, so let me tell you some of the things we know. First, as I said, evil primes exist. It's already clear from van Wemelen's computations. The second question is, can we bound the primes? So Kristin and myself obtained the following theorem, that if you present your field in this form, Q square root of D square root of R, so it's a primitive CM field, where D is just a positive integer, so that's the totally real subfield, square free. And to obtain a CM field, you join the square root of R, where R is a totally negative number in this field. So you present your field this way, and then you can show that if P is an evil prime, then it satisfies this bound. We know from numerical data that this bound is not optimal, but it's somehow in the right sort of area of being optimal. It's not too far from that. Okay, so that's one result we have. And another theorem was that, in fact, evil primes can exist in abundance. So basically, it tells you that if you take a block of rational primes, they could all arise as evil primes for CM fields. The whole block will arise simultaneously as evil primes for a suitable CM field. So there could be as many of them as you want with any type of configuration and so on as you want. So that's a more technical statement that tells you that, in fact, if you pick a set of primes, it gives you conditions that all primitive CM fields satisfying those technical conditions and whose discriminant is big enough will have the property that those primes as are evil primes for them. Okay, so the short way to think about it is you give a block of rational primes for all big enough CM fields satisfying some conditions, but infinitely many such CM fields, all those primes will be evil. Okay? So it really means that the most important question here is to understand what are those evil primes. And we don't really know, but what we know is to translate it into a problem in algebra. So we can relate the problem to a problem in algebra. So remember that to have an evil prime was to say that I have an abelian variety with complex multiplication, which is mod P isomorphic to a product of elliptic curves with the product polarization. Okay? So if we can write those elliptic curves explicitly in some way, it means that the ring of integers of this CM field, this OK, would embed into certain algebra. This algebra describes the endomorphisms of a pair of elliptic curves, E1 times E2. But it doesn't just embed into it in any other way. We know this happens infinitely often. It embeds in it in a way that the natural involution on this algebra, coming from the fact that the polarization is lambda 1 times lambda 2, induces complex multiplication on OK. Okay? And it turns out, well, first we could prove that the converse is also true. Namely, if you have such an embedding, such that the natural involution on this algebra induces complex multiplication on OK, then P is evil. So we can construct then an abelian variety with Cm by OK in characteristic 0 that reduces mod P to a product of elliptic curves with the product polarization. So the problems are equivalent. And then the issue, therefore, is to analyze this problem, which we still don't know. What is clear is that you can write exactly what it means to embed this algebra here, satisfying the conditions on the involution. I mean, after all, those are just 2 by 2 matrices. Okay? So you can write it down, and you get a bunch of equations. But we couldn't really analyze those equations well enough to determine exactly what are the evil primes. Namely, we couldn't give a criterion, a necessarily insufficient criterion for being able to solve those equations. We could just show that if P is big enough, that's not solvable. You cannot solve the equations, and therefore, if P is bigger than this D squared raised R squared, you cannot solve the equation, so it cannot be an evil prime. Okay, so what time should I finish? No, okay, that would be 10 minutes maybe? Too much, yeah. Okay, so let me see what I want to tell you about the proofs. Not too much, actually. So let me tell you really the idea coming into the proof. Okay, so the idea is to try and use, so having presented our field K as Q square root of D square root of R, we need to understand what does it mean to embed square root of D into such an algebra, and what does it mean to embed square root of R into such an algebra, under conditions that the involution on this algebra induces complex multiplication. So here, so it means that square root of D should be fixed under this involution, and square root of R should go to minus square root of R. Okay? But you can write it down. The point then is to try, or what we are able to do is to analyze those conditions and show that in fact the entries of the matrices and by defining such an embedding must be small, where small really depends, so the size is bounded by data coming from the CM field K. Okay, that was the main thing to do. Okay? Somehow by analyzing those equations, messing around with them, show that the size of the entries, so those are elements either in a quaternion algebra or something very close to a quaternion algebra that's a certain ideal, have bounded norm, where the bound depends only on the field K. Okay? But that means that, so if the prime P becomes very large, it means that somehow the size of those elements is very small compared to the algebras that appear here. I mean, this is an order in the quaternion algebra ramified in P and infinity. Okay? So morally talking, you should think about the case where E1 is equal to E2, where you just have OK embedding into 2 by 2 matrices with entries in a maximal order R of this quaternion algebra BP infinity. Okay? And what we show is the following lemma, that if we have two elements in this order whose norm is small enough compared to P, then the elements commute. All right? That's the key point. Analyze the equations to get a bound on the entries, which depends only on k, and then let p grow, so it becomes very small compared to p. It satisfies this bound. But then if they commute, it means they all lie in some quadratic imaginary subfield of this quaternion algebra. Okay? Those are the maximal commutative subalgebras of BP infinity that corresponds to some. So all the entries lie in a single quadratic imaginary subfield here. So what you find is that OK actually embed to M2 of some K1, where the field K1 is this quadratic imaginary subfield. But that, again, produces a contradiction because it implies K is not primitive, as we've used before. Okay? So I think that's what I want to say about the proof of Theorem 1, and I'll just skip the rest. Yeah. So somehow it's hard to okay, let me see what I can tell you here. Okay, now not much. Okay, let me skip ahead and say a few words about the work of Bruinier and Yang. Okay. So, another way to, or the theorem or the proof of what I actually showed is related to the theorem of Gross and Zagier. Okay, so I'll skip back for a second. You see, we got this condition here, this lemma. Okay. It turns out that this lemma actually implies a weak form of the Gross-Zagier theorem. Okay? So I'm just trying to take out the thread here. Okay? This lemma somehow has to do also, or it implies a weak form of the theorem of Gross and Zagier. The theorem of Gross and Zagier takes this function, j tau 1 minus j tau 2, letting tau 1 and tau 2 run over imaginary or over representatives for imaginary quadratic fields satisfying, the discriminants are relatively prime. And it gives a closed formula for basically what you see here is the norm of the difference j tau 1 minus j tau 2. When you take the norm, it's the same as taking the product over all tau 1 and tau 2, where tau 1 runs over the singular moduli for K1 and tau 2 runs over the singular moduli for K2. And it gives a closed formula for that in the following form, where this function is readily computable if you have an integer m. Typically it will be 1, and otherwise it would be a product of a single prime, L, where they can say exactly when this happens. Now, so I want to say something about the work of Bruinier and Yang, which is really introducing new ideas into this game. So they looked at this formula of Gross and Zagier, and they thought about tau 1 and tau 2 not as living in the upper half plane, but in fact in the upper half plane times itself. So they're thinking about them as tau 1 lying in the modular curve x1, which is h modulo SL2z, and tau 1 lying here. But then they think about this as the moduli space, or sort of the modular surface of h2 modulo SL2z plus z, where that just means SL2z times SL2z. Okay, just a way to write it. And they think about the result of Gross and Zagier as giving the arithmetic intersection number of, or more precisely of the Galois orbit of this point, tau 1, tau 2, with this diagonal x1 times x2, because the diagonal measures when is tau 1 and tau 2 belong to, give you the same elliptic curve. And taking the intersection is really counting for each prime p, or looking for each prime p, whether the two elliptic curves associated with tau 1 and tau 2 become isomorphic or not. but that means that J tau 1 is congruent to J tau 2 mod P. Okay, so they can translate the issue of looking at such a product of J tau 1 minus J tau 2 into an arithmetic intersection number. Okay, so also in that sense, it's kind of a similar flavor to the problems we were discussing in the context of class invariants. Okay? And in fact, already in their paper, Gross and Zagier don't just look at the diagonal, but they look at the graphs of the Hecke correspondences. The Hecke correspondences, say TP, are multiple valued functions from x1 to x1, but they have a graph in the product, x1 times x1, and you could ask, well, what's the intersection number of a point tau 1, tau 2 with such a graph? And from this perspective, Bruinier and Yang viewed this situation of Gross and Zagier as a degenerate case of the following case, that you take a totally real field, you look at this Hilbert modular surface that we discussed before. The Hecke correspondences are now replaced by the Hirzebruch-Zagier divisors we mentioned before. And the good functions are Borchardt lifts, as I've mentioned. And in fact, if you go back, one finds that this J tau 1 minus J tau 2 is in fact, again, a special case of Borchardt's theory. It corresponds to the lift of the function J tau minus 1744. Okay, so some of the whole structure present in the case of Gross and Zagier's work on singular moduli also is present in this situation. And the CM points now are coming from primitive quartic CM fields containing L. So the type of CM fields we are looking at. And okay, to say it shortly, they look at very special, the result only applied for very special CM fields, K. And what they do, they take good modular functions on the Hilbert modular surface. So their divisor is a combination of the Hirzebruch-Zagier divisors. Okay, so it's vast generalization of looking at J tau 1 minus J tau 2. And they have a theorem. So you see there's a lot of data in this theorem. So instead of reading it, let me tell you the executive summary. If you take such a function and you take the value, you take the product of its values on all the CM points associated to a primitive CM field. It's the analog of taking the product of J tau 1 minus J tau 2 over all couples tau 1, tau 2. Okay, so you have now a primitive quartic CM field. You take the product of all the values. They are able to give you its prime factorization. Okay, so it takes a little bit to trace through all of that. But in the end of the day, what you find is once you exponentiate it and square it, that you can, this formula becomes, you see, if you go all the way down, and you look at this expression and you exponentiate it, you find a prime L there. Okay? So it's analog to Gross-Zagier writing the product of the J tau 1 minus J tau 2 as a product of this FD minus X squared over 4, where those, if you remember, those Fs were either one or a product of a single prime. So it's the same structure that they get. And you see that this actually suggests a general conjecture. They made the following fascinating conjecture about the intersection number of the CM cycle of K, so that's all the CM points associated with K, with the Hirzebruch-Zagier divisors. They gave a closed formula, a closed conjecture for this. And this is very much related to the problem that interests us, because, well, we were talking about the intersection of this CM cycle with the Humbert surface H1. Those were the evil primes. This intersection number is essentially the evil primes for K. We thought in the context of the Siegel space, but we can pull back everything to the Hilbert modular space, where the pullback of H1 is now a sum of Hirzebruch-Zagier divisors. And the intersection number is just, therefore, CMK with some of those divisors. So it's given by a sum of those numbers. So it's exactly the problem that interests us. The result is only available, I mean, our result applies basically for every CM field. They are putting very strong restrictions on the CM fields. But so there's some trade-off between what they can do and what we can do. But I like to mention that's a very exciting development that recently Tonghai Yang was able to prove this conjecture for, again, a very special class of CM fields. So this is still somehow developing and probably would take still a number of years until they can get the result that they want. But so there's some progress there that there's some progress happening. It's maybe in closing, and that's my last slide, I would just say that this would not answer the question we are looking for still. This tells you about the totality of evil primes for a CM field K. So all the primes P that sum a Abelian surface with complex multiplication would have this degenerate reduction. But what we would really like to know is, given an Abelian surface with complex multiplication, say it's associated with some ideal class for the CM field, what are the evil primes for that? Is there an a priori algebraic description for that? Because if you knew that, well, you would know a lot of things. You can construct units, for example, and so on. And that would be quite interesting. So I'm done. Thank you.